Okay, so let's talk about chapter 11.1, part 1. Okay, so we're still going to be talking about hypothesis testing. Chapter 9 introduced hypothesis testing. Chapter 10, we did confidence intervals and more hypothesis testing. Chapter 11 is hypothesis testing, but it's a different type of hypothesis test. And we start with the chi-square goodness of fit test, but actually there's 3 chi-square tests we do with testing 3 different types of claims. The first one, the goodness of fit test, tests a claim about a distribution of one categorical variable for a population. Okay, so this is very, very different from what we've been doing before. We've been dealing with quantitative variables like proportion and mean, and now we're switching to talking about categorical variables. In this case, the categorical variable we're talking about is color. Okay, so since we are not doing this activity together, which usually is a highlight of third quarter, unfortunately we can't do that right now. So, excuse me. So I'll draw you a little picture, kind of what the point of this activity was and how we're talking about M&Ms and colors and things. So the point of this was that the Mars company who makes M&Ms claims that these are the percentages of the distribution of the colors of M&Ms in any sample. That's what you should see, or in the population, that's what you should see, I should say. This is a claim about the population. Okay, and so if you take a sample, a big random sample from the population, you should see something similar to this. That's the idea, at least, if what they're saying is true. And so a chi-square goodness of fit test does this. It takes the population. Let's say this is the population. Okay, and the claim about the population is that there's a distribution of a particular categorical variable called color, in this case for M&Ms, and they're saying that they have a specific distribution. So let's say they're saying brown and red should be 13%. So let's say this is brown and this would be red, the smaller ones. And then you'd have a bigger distribution, let's say yellow, bigger part of the population, and then greens, green here and orange, and I don't have one for blue. Okay, but that's okay. So the point is that all of these colors are part of the color categorical variable. Okay, so they are values of the color categorical variable. And so we're asking, there was a claim by the company that says this is the distribution of color for the population of all M&Ms. Okay, so they say that this is how we manufacture M&Ms. And what we want to do is test that claim by taking a sample and seeing how does the sample data fit with the claimed data. Right? That's basically what we're doing. The difference is when we did a test for means, we had 1 mean or 2 means. When we did a test for proportions, we had 1 proportion or 2 proportions. Here we're testing one categorical variable, but the value of the variable can take on many, many different things. So it's not just 1 proportion or 2 proportions. Here we're saying there are actually many proportions in the population that we're testing all at the same time. Okay, so it's quite different from a regular proportion test. And students are tempted to say, well, we've done a test for a proportion, so if the proportion says that 13% must be brown and red, then I can just do a proportion test here and a proportion test here, and that's kind of the same thing, but it's not really the same thing. You have to take into account all of the proportions at the same time. Okay, so it's like doing 6 proportion tests all together at the same time. That's what a chi-square test is. All right, at least goodness of fit test for this specific example is like doing many proportion tests together. you can't separate them into individual tests because all of these quantities affect one another, so they're related to each other. Okay, so it's very, very different from tests for one proportion or a difference in proportions. All right, so any case, that's kind of the gist of chi-square goodness of fit test. It's kind of the gist of it. So I'm going to walk you through this, and hopefully by the end of the note sheet you'll have a little bit of a handle on chi-square goodness of fit test. Okay, we'll actually just do quite a bit of an intro today, and then next time we'll do a formal chi-square test for goodness of fit. Okay. All right, so let's assume this is complete. Then this is the claim from the company, Mars, about the distribution of M&Ms. And so we took a sample. So in class we would have taken a sample, but let's say we took a sample and we got 13 blue M&Ms, 10 orange M&Ms, 2 green M&Ms, 9 yellow, 10 red, and 2 brown. And our bag of M&Ms consisted of 46 M&Ms total. Okay, so we're just saying this is the claim from the Mars company, and we went and took an actual random sample. Now, what we actually did is just bought a bag of M&Ms. That's not necessarily a perfect representation of a random sample, but that's what we're going to consider our random sample. We bought a bag of M&Ms, and now we're going to analyze that bag of M&Ms and compare it to the claim that Mars company made. All right? And so that's my observed M&Ms in the bag. This is how they were distributed. All right? Now we want to say what should have happened if what the Mars company claimed is correct. So they said there should be 13% brown and red. Okay? So red and brown should be 13%. So if I said here's my total number of M&Ms, then if I take a sample, what should happen is that 13% of that sample should be brown and 13% should be red. So we literally just calculate those numbers, 13% of the sample size. Okay, so we say 46 times 0.13. That is what I'm expecting to see if we assume that Mars company claim is true. Okay, and then brown and red are the same, so 46 times 0.13 here, and you get 5.98 and 5.98. And then we do the same for the rest. So they said there should be 14% yellow, so we say, okay, so my sample times 14% should be what I expect to see for number of yellows, 6.44. And don't round this. It's tempting to round this, like how can I have 0.44 of an M&M or something, but don't round this, just leave it like that. Okay, and so on and so on. So if we do green, the percent was 16, so 46 times 0.16, and I think if you do that you get 7.36. And then orange was 20, so 46 times 0.2, and you get 9.2. And then the last one was blue, 24%. So you should see the most blues. Interesting that they chose blue. I'm not sure why that one's so popular. But in any case, times 0.24. And then you would see 11.04. Okay? So observed is what I saw in the sample that I took. Expected is what I should see if the claim of the company is true. Okay, so now you can see, you can kind of do a comparison, just a visual quick comparison, like this is what I expected to see and this is what I actually have. This is what I expected to see and this is what I actually have, and so on. So green looks a bit questionable, and maybe brown looks a bit questionable in my sample, and maybe red is also too high or something like that. So you can see some quick relationships there, okay? And of course, what should happen if you rounded, I mean, you'll sometimes end up with slightly less, but if you did this correctly, calculated your expected values correctly, then what you should get is 46 if you total all of those numbers up. Okay? And then how the chi-square statistic works. So here's the formula for chi-squared, and we would have done this together in class if we had, try to figure it out ourselves if we did the M&M activity, but there's the chi-square statistic. So we're trying to calculate that statistic. So now what we do is we say, take observed and subtract expected from it. All right? So observed minus expected, and so what we're doing here is just literally that. I'll write out the first one, I guess. It's 13 minus 11.04, and what you get is 1.96. Okay? And so on. So you do 10 minus 9.2, and then you get 0.8, and so on. So the rest of them I'll just write down. So you subtract these two, you get negative 5.36, 2.56, 4.02, and negative 3.98. Okay? And if you add up observed minus expected, if you add up all these numbers, you get 0. All right? And then, so that's not very useful for us to get a statistic that becomes 0. All right? So that's why statisticians said, let's square this. And then students always ask the question, why not just take the absolute value? And if you take calculus, you'll learn that absolute value functions are not fun in calculus because they look like this, and this point of the function is not differentiable, so it generates a function that's troublesome for some of the higher mathematics that people do with statistical calculations and proofs and all those kind of things that we don't see. So suffice it to say that we use a quadratic function because it's nice, looks like that, and that's why we square and not take the absolute value, because this function is much nicer in calculus, okay? It's differentiable everywhere. In any case, that's a slight explanation of why we square and not take absolute value. And then you do this and you square it. So if you square this number, it's 1.96 squared, and you get 3.8416. And of course, the more decimals you leave behind the decimal point, the better for your accuracy, okay? And if you square 0.8 squared, you get 0.64, and so on. So you get 28.7296, and then 6.5536, 16.1604, and 15.8404, something like that. All right, and I'm not sure if it's valuable adding up this number. I have it, but I'm not sure if that's important. Okay, and then finally, so all of this stuff was numbers we calculated on our way to come up with some kind of a number that represents the whole situation all taken together. Okay, so we want, just like we used for our hypothesis testing, we have a z or a t value that we then use to calculate probability on a distribution. We want to here have a summary of all of this stuff taken together, and that is what we call chi-squared. Okay, and we'll see that in a second. So if we take this observed minus expected squared over expected. So what I'm doing now is I'm taking 3.8416 and I'm dividing it by what I expected, right, which is 11.04. All right. So what I'm getting is a number that's this 0.34797. So that is a comparison of how far away my observed and expected were away from each other, and then I compare it to what I expected to see in the first place. Okay? And so you keep doing that. So this one would be 0.64 divided by what I expected, which was what was my expected? 9.2. And so you get Is that right? 0.6, and so you get 0.69565. Okay, so observed minus expected squared, which is this number, divided by the expected number, which is 11.04, and here's 9.2. Wow, I better check myself. I don't know why I'm feeling like this doesn't quite work. This is not the right number. I missed a digit here. Okay, if you do that division, you get 0.0695. 957. Let's say like that. Okay, so that's actually what you get. And then if you keep doing that, the same calculation, take this number, divide by this number, and then you get some number. So this is 3.903478, and I apologize for how tedious this is. It's pretty tedious right now, but there's a faster way to do all this. Okay, of course you'll see your calculator does all this stuff for you. So 2.7024, and then 2.648896. Technically, you need to do as many decimals as you can to be more accurate. And if we add up all these numbers, okay, so this is kind of a measure of how far away is the blue from what I expected compared to what I expected. This is a measure of how far away is the orange from what I expected relative to the expected, and so on. So if I add up all those numbers, what you end up with, I think, is about 10.689957, something like that. Okay, and this number is a summary of everything taken together. Okay, and we call that number chi-squared. That's called chi-squared. Okay, so this would be our test statistic. That would be our test statistic. Comparing my observed data to my expected data relative to the expected data for each category of the color, okay, the categorical variable color, and then I add it all up, and that gives me my chi-square statistic. And now we know what we do with the test statistic. We take the test statistic to the distribution, and then we calculate the probability that we would get that test statistic, or one that's more extreme. Okay, now the problem is, so we've been doing this with T and Z. Z is normal, T is student, T distribution, and we would put our Z value on here, and then we would calculate our probability. Okay, and T distribution was very similar, maybe more spread out. Remember, I say it's more spread out, but then you take your T value, you put it on here, and you find out what's the probability that this happens. Okay, so that was kind of our procedure. Now, the question is then, what type of distribution do I have to put the chi-square statistic on? Right, and so we'll see that in a few minutes. All right, so let's talk about how do you write hypotheses. So again, hypothesis test is the same. You assume that the claim is true, you write your hypotheses that way, and you do your test that way. Okay, so remember, inherent in this was our assumption that the Mars company's claim was true, and that's these numbers right here. This is my proof that I'm assuming your claim is true. That's the part of the statistic. Okay, so how you write this is, there's two ways you can write this. You can say the null hypothesis is their claim distribution is correct, and the alternative hypothesis is it's not correct. All right, that's one way. Or you can write your hypotheses this way and say the null hypothesis is that the proportion of blue is 0.24, orange is 0.2, and list all the proportions that they claimed. And then the alternative hypothesis is that at least one of those are incorrect. And if one of them are incorrect, then we know at least two of them are incorrect. And so that's, if one of them are incorrect, the whole claim is out the window, basically. So if one of these are incorrect, then I can say that I will statistically significantly incorrect, and I will reject a null hypothesis. Okay, so you have two choices for writing your hypotheses. Some students like this, some students like this. Either way, it's fine, as long as you define your P variable. All right, so with P sub blue and then P sub color, what is it? All right. Then it says, don't state the alternative hypothesis in a way that suggests that all the proportions in the hypothesis distribution are wrong. Yeah, so just say at least one of those are incorrect, because one of them actually could be correct. So you can't say all of them are wrong. One of them could be correct. Okay? And I think you can see here that we got fairly close to one of them being correct. This was a fairly close. So it's possible that one of them are exactly correct. So you can't say all of the proportions that I hypothesize are incorrect, just one. Okay? So, I think what we're going to do now is walk back slowly through again how to calculate the chi-square statistic for a different scenario, so it's not based on our sample we supposedly took together in our activity, which is what this is for. We'll walk through this again slowly, make sure you get it, and then we'll talk about what a chi-square distribution looks like. It looks kind of like this, very, very heavily right-skewed. And then we'll talk about maybe some conditions, and we'll calculate a probability from that. Okay? So, again, how this works is we go here and we say, here's a hypothetical person, Jerome, who took a sample and got of 60 candies. And we're saying calculate the expected values. So here's what Jerome saw in his bag. This totals 60. All right? And so now we want to go and do the same thing. I want to use Mars Company's claim and compare and calculate what should have happened if their claim is true. I'm going to assume their claim is true. So I'm assuming that their claim for blue is true, which is 0.24. And then I'm going to say I'm going to multiply that by 60 in my sample. And that means this is what I should have seen if their claim is true. Okay? This is what I saw. This is what I should have seen if their claim is true. All right? Obviously, you know at this point, the further away what I expect from what I observe, the more unlikely it is that this is just a coincidence, and that more likely it is that I'm going to get a statistically significant result. Okay? And so I just go through and believe their claim, 20% times 60, and if I believe their claim, I should get 12. And then if I do 16% times 60, if I believe their claim, I should get 9.6, and so on. So you just go through and do the whole set of calculations again, assuming that this is true. Then you get 8.4, and if this is 13%, and this is 13% like they said, then I get the same thing twice, which is 7.8. Okay, so now I have my list of expected values. Okay, what did I expect to see if what they said was true, their claim was true? Okay, and so this is on your formula sheet. I just make a note for yourself. This is on the formula sheet. Okay, on the formula sheet. Yay! All right. So you don't really have to memorize this. More important that you know how to use it. And actually, this chi-square statistic is the same. It doesn't work. You don't calculate it the same, but it's the same formula technically for all three of the chi-square tests. Okay. So chi-square statistic is a measure of how far the observed counts are from the expected counts. Makes sense. How far are they from each other? And then, of course, relative to what I expected. All right. And that all makes a lot of sense. If you think about it carefully, that actually makes a lot of sense. So there's the formula. Chi-square is do observed minus expected, square it, divide by expected, and then you get a number, and you add up the number for each color, each value of the categorical variable. Okay? And so that's the formula. And then we can do it. So let's calculate the chi-square statistic for Jerome's sample. All right. So here we go. So chi-squared is, all right, and we're going to just list the numbers. So observed minus expected. So we go to the first color, which is blue, and we say observed minus expected. So 9 minus 14.4 squared divided by what I expected, 14.4. All right, plus the second one would be orange, and that's 8 minus 12. So 8 minus 12 squared divided by what I expected to see. All right, and so on. So I'm going to do all of this with you. I'm not going to go reference that again because I think you see the pattern here and you're faster than I am probably. But yeah, so this is what you do to calculate the chi-square statistic. Kind of tedious. Okay, and you won't have to do all of this on an actual exam because showing repetitive stuff like this is not too useful. What we will do is show you how to shortcut this a little bit. But for now, we're trying to just understand exactly how the chi-square statistic is calculated. Okay? And then you get chi-square is, and the next numbers are actually important numbers. If you calculate this manually, you end up with these numbers. Now, for a goodness of fit test, I think your calculator gives you these numbers. Okay, so you don't have to manually do what we're doing here every time, but these numbers are important. 186 plus 0.621 plus 0.415. Okay, and if I add all that up, you get 10.180. Okay, so there's my chi-square statistic. So I did it. All right. This one number for Jerome describes how all of the observed and expected counts fared relative to what I expected. Okay, so how they relate. And I have a number that quantifies that whole scenario. All right? So, again, think of chi-squared there. Yeah, I think I said that. You can read this if you want. And then they ask the question, why am I dividing by expected? And this is good to read. I would go read that if I were you. It clarifies some things if you're confused at all. To me, this now makes so much sense, but it took me a few years to come up with a feeling of satisfaction here. Okay? And then, okay, so now I've got a chi-square statistic of 10.18. What does that mean for probability? All right, so what they did here, hopefully you understand what this thing is. This would be them saying, assuming H sub 0 is true, let's build a approximate sampling distribution. Okay, so they took 500 samples of size 60 from a population that is distributed the way that Mars said that is. So they made a fake population, okay? So they made a fake population. Let me draw a fake population here, okay? And they distributed it exactly the way that Mars said, okay? And from that fake population that's distributed exactly correctly according to Mars's claim, they took 500 random samples of size 60. And then they calculated a chi-square statistic for each sample. So what they did is here, I take a sample of size 60. So here's my sample of size 60, okay, from the population, randomly selected. And then I take that sample and I calculate a chi-square statistic just like we did. Just like we did right here, okay. Calculate a chi-square statistic, and then you plot it. Boop. So here is one chi-square statistic. And that one is maybe just above, what's that? 2.5, maybe that's like 3 or something, okay? So this is a chi-square statistic that's about 3, all right? And so on and so on. Here's a chi-square statistic that's about, I don't know, what's that? 22.5, so maybe like 23.5 or something like that, I don't know. 24, something like that. Okay? And so just remember, this is an approximate sampling distribution. Okay, and we can use this approximate sampling distribution now to go and evaluate the company's claim. Okay, so we did a simulation, and we can use our simulation to evaluate the company's claim. So we know how this works. What we do is look for chi-square statistics that are as extreme as ours, 10.18, or more extreme. And so they put the line here for us. That's beautiful. This line is 10.18, okay, as a chi-square statistic. So these are all the chi-square statistics that were 10.18 or more extreme. And so for our sampling, approximate sampling distribution that we created, we just count the dots. Okay, now, I mean, this is hard to count because they're not stacked properly. That looks kind of weird. But let's trust them. They said that if you count these dots, what you get is 37 dots. So 37 simulations led me to a chi-square statistic that's 10.18 or bigger. And 37 out of the total 500 simulations is about 0.074. Okay? So this would be my approximate p-value based on my approximate sampling distribution. So again, now you know what to do with this. P-value of this, we compare it to a significance level, and that says that this p-value is bigger than our significance level, so we don't have enough evidence to reject their claim. So at this point, based on this, we would just believe the Mars company and say, okay, I can't say that you're wrong. I'm not accepting your claim. Remember, we don't accept claims, but I can't say you're wrong. I don't have evidence to say that you're wrong. So that's it. All right? Now, this is great. There's a distribution. So, okay, you remember that for normality, we have a normal condition, okay, to confirm that the distribution is approximately normal, and that is for means. We have the CLT. That means that my sample size is greater or equals to 30, and I don't have any visible outliers. And for proportions, I shouldn't put equal, let me put an arrow there. We have the large counts condition. So NP greater or equals to 10 and N1 minus P greater or equals to 10. Okay, so CLT, and this is large counts condition. So what is the condition that I need to ensure that my distribution will follow approximately a chi-square distribution? My sampling distribution will follow approximately a chi-square distribution. And as you can see, please, this is normality for means and proportions. Chi-square is absolutely not normal, very heavily right-skewed distribution, but we can still calculate probability from there, like I just showed you. So here's our condition. When the expected counts are all at least 5, the sampling distribution of the chi-square statistic is close to a chi-square distribution, with degrees of freedom equal to the number of categories minus 1. What does number of categories minus 1 mean? It's this. How many colors were there? Okay, so blue, orange, green, yellow, red, brown. 6 categories, 6 values of my categorical variable. And so for us, our degrees of freedom would be 6 minus 1, which is 5. Okay, and the 6 is the individual colors in our scenario. So your condition to check for not normality for a chi-square distribution in this case is this expected counts. Expected counts are all at least 5. Okay, expected counts, not observed counts. Expected counts. Okay, so chi-square distributions are a family of density curves that take only non-negative values. So there is the smallest chi-square value I can possibly have is 0, and then I get bigger values. Okay, so that's it. And then a particular chi-square distribution is specified by degrees of freedom. Okay. Just like t-distribution, there's degrees of freedom for each sample size, or in this case, for each number of categories of your categorical variable. And the chi-square test for goodness of fit uses a chi-square distribution with degrees of freedom equals to the number of categories minus 1. And what they're showing you here is very heavily right-skewed distribution for smaller categories and much less right-skewed distribution for higher degrees of freedom. Okay, so as the degrees of freedom go up, the distribution will become more symmetrical, but probably not going to happen anytime soon. It's not going to become symmetrical anytime soon, because having this many categories in your categorical variable doesn't happen too often, at least not in our simple examples. Okay, maybe in other examples they do. All right, so yeah, all right, so hopefully this makes sense to you. We had a similar graph for the t-distributions. All right, so in the last example we computed Jerome's chi-square statistic. Let's find the p-value and its interpretation. Okay, so let's interpret the p-value. All right, so find the p-value and interpret. So we can say this. Since we have to actually go and inspect something. Since the expected values, and here they were, here are the expected values, all right? Here's my expected values, all of these. Okay, since they were all at least 5. Now what you have to do to satisfy this for, let's say, an AP exam is you have to list all the expected values. So you'd have to say something like this. You'd have to say since the expected values are all at least 5, okay, and then you'd have to list them. You'd have to say in parentheses, here are all the expected values: 14.4, 12, 9.6, 8.4, 7.8, and 7.8. So you're proving right here that all the expected values are at least 5, and then you would say the chi-square statistic. Okay, the chi-square statistic will follow approximately a chi-square distribution. Okay. The chi-square distribution when the null hypothesis is true. And more specifically, a chi-square distribution with, what is this, 1, 2, 3, 4, 5, 6, 5 degrees of freedom. Okay, so you'll say since the number of categories is 6, our degrees of freedom equals 6 minus 1, which is 5. Okay, and now I can do this. We want to say, okay, let's calculate the p-value. So we just did the conditions checking to say that the distribution is approximately chi-square. Okay, so now I know it looks something like this based on my expected counts, all expected values, all being at least 5. And then I go, okay, now I have to calculate the p-value. What's the probability? And please check this out. Chi-square is always greater than, okay, or equal to. We don't really do less than or equal to. We're always checking, here's my chi-square, and what's the probability that it's that big or more extreme. Okay, so chi-square is slightly different in that regard. Chi-square is greater or equal to the one we actually got, 10.18. And this is on your calculator. It's called chi-square CDF. Okay, so you go second distribution, and chi-square CDF is there, and you enter always the lower bound, and a good upper bound is 10,000. That's why we've been doing this all year. The 10,000 number comes from here, that we've been learning about 10,000. Okay, and then you put your degrees of freedom. So we will do this. Please don't write this. I'm just writing it down here to help you. chi-square CDF. Okay, this is what you'd enter in your calculator. Your statistic, 10.18, your upper bound, which is 10,000, and then your degrees of freedom. Okay, and that would give you about 0.0703. Now that's interesting. From our approximate sampling distribution, from our simulation, we got 0.074, and here we got 0.073. Interesting. Just gives more power to that idea of using simulation to approximate p-values, right, and approximate the real world. Okay. Any case, so there is a table for this. There's a table for this. Okay. I highly recommend that you don't use the table, right? Just use your calculator. So you'll see next time we'll do a statistical test together, a formal one, and there's a test on your calculator, stat tests, and it's called chi-square GOF test, okay? So I would not use the paper table for this because you have a calculator. That's better than that. All right? But I realized we didn't do the second part. It's interpretation. All right? What would be the interpretation? We would say what? The probability, assuming that the null hypothesis is true, meaning what? Assuming the null hypothesis is true, or let's not write that. Let's say assuming that the claimed color distributions are all correct, okay, of getting the color distribution we got, okay, from our sample is 0.0703. Okay, probability assuming that the claimed color distributions are all correct of getting the color distribution we got from our sample is this. Or alternatively, assuming that the color distributions are all correct of getting the chi-squared statistic of 10.18 or more extreme is that. Okay, which technically these two mean the same thing. Maybe this makes you more comfortable, the bottom one. All right. So I'm not going to do a video on this to find the calculator tutorial. I think that's pretty easy. You can figure that out. And there's your homework, slight little homework, delicious homework. Okay.